Hello everyone and welcome to a new video in the three-phase systems course, Unbalanced Three-Phase Systems Part 2. So what are the contents of this video? Analysis of star-connected load with neutral wire has an impedance using analytical method and verifying this method using MATLAB Simulink. Also, we are going to have analysis of a star-connected load with no neutral wire using different analytical techniques such as loop equations, nodal analysis, and star-delta conversion. And these techniques are guided by MATLAB M-Code and verified through MATLAB Simulink. Unbalanced star load with neutral wire impedance. As shown in the figure, we have a star load. ZA is not equal to ZB, is not equal to ZC, so the system is unbalanced. So definitely we have a neutral current. But the neutral wire now has an impedance ZNN, N small letter, N capital letter. So N small letter is connected to the ground. Definitely N capital letter has a certain potential. So the source voltage is balanced, so VA equals V angle 0, and definitely VB and VC are shifted 120 degrees. So our target is to find the currents IA, IB, IC, and then to find the power P, Q, and S. So the problem we have now that the potential of point capital N is not equal to the potential of point small letter n is not equal to 0. So we have a certain voltage here is called Vn. So how to find Vn? If we know Vn, we can solve the problem where the current IA equals VA minus Vn over ZA. So how to determine the potential of point N? We are going to use what we call it nodal analysis. If you don't remember the nodal analysis, let me remind you about it. If we have a circuit like this one, simple circuit, we have source V1, source V2, and we have some impedances. We need to calculate the current I in the impedance Z. So we can solve this circuit using different techniques: mesh analysis, loop analysis, superposition, Thevenin theorem, and nodal analysis. So how many nodes we have in this circuit? We have this one is a node, we are going to call it V, and we have another node here, and we are going to choose that one is our neutral point or ground. So we have one variable in this problem, V. If we know V, we are going to know the currents everywhere. So our target is to calculate the current I. But what is the current in the impedance Z1? We have I1, and the current in impedance Z2, we are going to have I2. So we are going to apply Kirchhoff current law, where the potential V is the highest potential in this circuit. This is our assumption, that we have potential V is the highest potential. So I1 plus I2 plus I should equal 0. So let's apply in the equation how to calculate I1. So I1 is V minus V1 over Z1. So that one is I1. So what's I2? V minus V2 over Z2. What's IV over Z? So I1 plus I2 plus I should equal 0. Once you calculate that one or you solve this equation, you are going to find V. Once you know V, you can calculate the current I. So we are going to apply the same concept in our problem. Three-phase circuit with neutral wire has an impedance. This is a network we'd like to solve using nodal analysis. Three-phase system with neutral wire has an impedance. If we know the potential of the point N, we are going to calculate the current everywhere. So we are going to use the nodal analysis for that one, assuming that the potential of point N is the highest potential. So for example, the phase A current is Vn minus Va over Za. We are going to apply Kirchhoff current law here, where Ia plus Ib plus Ic plus I neutral equals 0. So how we are going to apply that one? We are going to assume the potential here for that one is the highest, as we mentioned, and then Vn minus Va over Za, that one represents Ia. Vn minus Vb over Zb, that one represents Ib. Vn minus Vc over Zc, Ic, and plus Vn over Z neutral, that one equals 0. So we are going to rearrange this equation. So we are going to have V neutral point equals VA over ZA plus VB over ZB plus VC over ZC, and the denominator will be 1 over the impedances. We know that Y, the admittance, equals 1 over Z, so we can write this equation as VAYA plus VBYB plus VCYC over YA plus YB plus YC plus Y neutral. If we know Vn, so we are going to calculate the current everywhere, and then you are going to calculate the power P, Q, and S. To confirm the concept, let us take an example. For the three-phase network shown in the figure, the RMS voltage is 220 volt. We need to calculate the phase current, neutral current, and supply power P, Q, and S. So definitely the circuit is not balanced. We have different impedances here. We have ZA equals 14 plus J20. So that one is rectangular form. We can calculate it in a polar form. ZB is a pure resistance and ZC is a pure capacitance. And the neutral impedance is 2 plus J2 ohm. So how we are going to solve this problem? We are going to apply the nodal analysis technique. We need to calculate the neutral point voltage. We are going to apply this equation VAYA plus VBYB plus VCYC over YA plus YB plus YC plus YN. So we need to calculate the admittance. So YA is 1 over ZA and the same for B and C and N. So we have the values now. If we substitute in the Vn equation, consider that the voltage is magnitude and angle. So Vn is 66.5. Now we can calculate the currents. For example, Ia equals Va minus Vn over Za equals 9.11 angle minus 37.75 degrees. And Ib equals Vb minus Vn over Zb. And Ic equals Vc minus Vn over Zc. So the currents are not equal in magnitude. So definitely we have unbalance. Now we can calculate the neutral current, which is Ia plus Ib plus Ic, but at the same time Vn over Zn. So we have the same magnitude if we use this equation or this equation, magnitude and angle definitely. So that one equals 23.58 angle minus 128.5. How we can calculate the power? So I square R. For phase A, Ia square R for phase A, which is 14 ohm. For phase B, Ib square R for phase B, which is 25 ohm. For phase C definitely is 0 because we don't have resistance regarding the Q. Ia square XL for phase A. For phase B definitely 0 because we don't have any reactive component. And for phase C, Ia square XC. Remember that for phase C, QC is negative value, negative 5.31 kilovar because we have capacitive component. So the power in the neutral, we have losses in the neutral as well. I neutral square R of the neutral and Q for the neutral is I neutral square XL. We have the same value because the impedance of the neutral is 2 plus J2. What is the power of the source? PA plus BP plus BC plus P neutral. So we are going to add all the powers together. And for the Q, we are going to add all of them together. Consider the sign. And definitely the total apparent power is root PS square plus QS square. Now it's time to confirm our results using Simulink platform. So let's go. This is a system we'd like to simulate. We have balanced three-phase source feeding unbalanced three-phase load and the neutral wire has an impedance. So let's look inside this one. So we have here RL 2 plus J2, but the MATLAB wants that one in Henry. So that one is 2 over omega 2 by F. So let's look for the source. We have three-phase source ABC. So let's click here. So that one is 220 root 2 peak amplitude. The phase angle is 0 and the frequency is 50 Hertz. What about phase B? For phase B, same amplitude but shifted minus 120. For phase C, we have the same amplitude but shifted plus 120, or you can write it minus 240. No problem. So I'm going to measure the currents of the supply. So IA, IB, IC, and then we're going to have three lines, line A, line B, line C. We're going to measure the phase voltages, line voltages, and if you look here, we have a fourth wire. That one is connected to the neutral point of the source, small letter N, and that one will be connected to the neutral point of the load through an impedance. That one is grounded at this point. Let's look for the load. So we have the three currents A, B, C. We are going to measure the currents, measure the load voltages, and we have the load here for phase A. We have 14 plus J20, so we are going to divide that one by omega. So that one will be the inductance in Henry, and phase B is 25 ohm, and phase C will be minus J15. As you know that the capacitance cannot be connected directly to the source in parallel, so we have a small resistance here, and that one will be 1 over XC omega, gives you the capacitance in farad. But let's look here for this point. This is the neutral point of the load. We're going to measure the neutral current in the measurement block, and then we're going to have that one, which is a capital N letter, will be connected to the neutral point of the source through an impedance. So let's run and see what will be the results. So the neutral voltage is 66.5 angle minus 83.4, which matches 100% the calculated one. What about the currents? Let's click here. So the currents are 9.1 ampere with angle minus 37.75, and the phase B is 6.85 angle minus 133.4. Phase C is 18.82 angle minus 55.4, which matches 100% the calculated one. What about these voltages? What are these voltages? We said that the supply voltage is balanced. That one is the load voltage. For example, the voltage 222.4 is VA minus V capital N. So the power is calculated here as 2.35 kilowatt, that one for the phases, minus 3.65 kilovar, 4.3 kilovolt ampere, and that one is the power lost in the feeder. We have 1.1 kilowatt and 1.1 kilovar. Let's look here for the neutral current. We have the neutral current 23.5 angle minus 128.4 ampere. So what about the source? So if we look for the source, we have the total power of the source, the power from the phases plus the power from the feeder, 3.4 kilowatt minus 2.55 kilovar and 4.3 kilovolt ampere. The current from the source matches the current in the load because we have a star connected load. So line current equals phase current. Let's return back to our slides. Unbalanced star load with no neutral wire. As we can see here in this figure, we have a balanced source voltage. So the neutral point of the source voltage is connected to the ground. And we have unbalanced three-phase load where ZA is not equal to ZB is not equal to ZC. And the neutral point of the load, we call it floating point because there is no connection between the neutral of the source and the neutral of the load. So how we are going to solve this problem? So different techniques can be used. The first one, if we're going to use loop analysis and Kirchhoff current law, so we are going to find the currents in these loads. Number two, we are going to find the potential of the point N. If we succeed to find the potential of the point N, we can calculate the currents as well. Or we are going to use a star delta conversion. We are going to seek the help from the circuit analysis to convert this star connection to a delta connection and find the currents of the source. Method number one, using loop analysis and Kirchhoff's current law. As we can see here in this figure, we have a line voltage VAB applied to this loop, so we can write a loop equation. So VAB equals IAZA. So if the current is going in this direction, give you a potential in this direction. And if IB is going through ZB, so we have a potential in this direction. So VAB equals IAZA minus IBZB. We're going to do the same for VBC and VCA. So VBC equals IBZB minus ICZC, and VCA equals ICZC minus IAZA. Added to that, using Kirchhoff current law, where IA plus IB plus IC equals 0. We can put these equations in a matrix form. We're going to choose any two equations of the voltages plus the current equation. So someone said that I'm going to choose the three voltages and put them in a matrix form. You are going to end up by 0 because the supply voltage is balanced. So choose any two voltage equations and the current equation. So I choose here VAB and VBC and put the current equation. In this case, you can find IA, IB, IC. So that one is the impedance matrix. So we can put that one as admittance where Y equals Z inverse. So in this case, we can write the equation that I as a vector equals Y multiplied by V. So we are going to use MATLAB M code to solve this problem. We can solve the problem manually, but it's doable, but takes long time and somehow complicated because we have polar and rectangular forms. But the MATLAB is going to solve the problem quickly and effectively. Method number two, nodal analysis. In this method or this technique, we need to find the voltage of the point N. If we succeed to find Vn, we're going to calculate the currents IA, IB, IC. So we are going to use Kirchhoff current law, where IA plus IB plus IC equals 0, and we are going to assume that the potential for the point N is the highest potential in the problem. So we are going to apply this equation, Vn minus Va over Za, so that one represents IA, and that one represents IB, and that one for IC equals 0. We are going to rearrange the equation. If we rearrange the equation, so the potential for the point N is VAYA plus VBYB plus VCYC over YA plus YB plus YC. Remember that Y equals 1 over Z. So in this case, we know Vn, so we can calculate the currents IA, IB, IC, where for example, IA equals VA minus Vn over ZA. Again, the MATLAB can help us to solve this problem. We can do that one manually, but we're going to do that one using M code. Method number 3, star delta conversion. As we can see here, we have a star load unbalanced. So if we succeed to convert that one to delta load, so we are going to solve the problem exactly like what we did in the previous video for unbalanced delta load. But the voltage here will be the line voltage, not the phase voltage. Remember, the source voltage is balanced. So if we have a star load like this one, we are going to seek the help from the circuit analysis to convert that one to a delta like this one. So we have ZA, ZB, ZC. So ZAB equals ZA plus ZB plus ZAZB over ZC. And you are going to do the same for ZBC and ZCA. So remember here, I do that one as a color coded just to make it easy for you to know how to convert from star to delta. So now we have a delta connection like what we see here. So in this case, we can calculate the current IA delta. The current here will be VAB, the line voltage of the star, over ZAB. And the current IB delta will be here, and the current IC delta will be there. So once we calculated the current here and current there, so we can calculate the line current of the delta, where the line current of the delta, phase current of the star. So if we have a current here, it's called IA, so that one will be the current going through ZA, our original impedance. So in this case, IAY equals IA delta minus IC delta, and the same for the other currents. So again, we can solve this problem using hand calculation, but we're going to do that one using M code as well. Example, for the three-phase network shown in the figure, the RMS phase voltage is 220 volt 50 Hz. We need to calculate the phase currents and supply power PQ and S. If you notice here, we have no neutral wire, and the impedance here, ZA equals 14 plus J20, and the impedance ZB equals 25 ohm pure resistance, and the impedance ZC equals minus J15 pure capacitance. So we are going to put the impedance in the polar and rectangular form, and also are going to calculate the admittance for each one. So we have ZA, we are going to calculate YA, YB, and YC. So what is the solution? We are going to start by method number 1 using loop analysis and Kirchhoff's current law. So we are going to build the matrix VAB, VBC, 0. So that one equals ZA minus ZB 0, 0 ZB minus ZC 1, 1, 1. So the voltage here is a line voltage. So don't forget the angle, 220 root 3 angle 30. And that one is 220 root 3 angle minus 90, and that one is 0. We're going to fill this matrix by the impedance values, and then we're going to find Y equals Z inverse, and then we can calculate the current. So again, as I mentioned, we can do that one using hand calculation, but that one is too long. This is the M code I built for method number 1. We entered in line number 9 the V phase voltage value 220 volt. Line number 11 we have line voltage 220 root 3. Then we are going to enter impedance ZA, ZB, ZC. So in line number 14 we have the voltage vector. So V line multiplied by e to the power j pi over 6. So that one is an angle 30 degrees. So the impedance matrix ZA minus ZB 0, 0 ZB minus ZC 1, 1, 1. So we can calculate the admittance, which is Y equals the function INV MZ. So that one is the inverse of the impedance matrix. Then we can calculate the current in line number 18. I equals Y multiplied by V voltage. So in this case, we are going to display here the results. So the currents will be in rectangular form, and the current in the polar form will be 22.5 ampere for phase A with angle minus 33.7. For phase B will be 7.3 ampere with angle 2.8, and for phase C will be 28.7 ampere with angle 154. What about the neutral voltage? I calculated the neutral voltage here, and if we look here, we are going to find that the neutral voltage is 353 volt, which is more than the supply voltage in this case. Severe unbalance for this problem. I didn't calculate the power in the software or in this code. I leave that one for you because the power is easy. P equals I square R, Q equals I square X, and S you can calculate it as root P square plus Q square. So here I just calculated the main part, which is the current. Once we know the current, we can calculate the power easily. If we like to solve the problem using nodal analysis method number 2, we are going to find the potential of the point N, where Vn equals VAYA plus VBYB plus VCYC over YA plus YB plus YC. So remember, the voltages here are phase voltages. Then we are going to substitute in this equation, find Vn. At that time, we can find the current. For example, phase A current equals VA minus Vn over ZA. And the same for phases B and C. So we are going to build an M code for this problem using nodal analysis. We are going to enter the voltages, phase values, and the impedance, as you can see in line number 9 and line number 11. And then we are going to calculate in line number 13 the admittance for each impedance, YA, YB, YC, and then the total admittance, YA plus YB plus YC. Then we are going to calculate the neutral voltage in line number 18. If you look here, so that one is the neutral voltage, the equation we used for the nodal analysis. And then we are going to calculate the currents in line number 21. So what are the results? We have the neutral voltage, the same results we got from the previous case or the method number 1, 353.7 volt angle minus 145.7 degrees. About the currents, we have the same values. IA, for example, 22.5 angle minus 33.7, IB 7.3 angle 2.8, and IC 28.7 angle 154.9. So now again, we can use the currents to calculate the power, but I leave the power for you. The power is I square R and Q equals I square X, and S either VI conjugate, or you can use root P square plus Q square. So we are going to solve the problem as well using star delta conversion technique. So we are going to calculate ZAB, ZBC, ZCA using the impedances we have, ZA, ZB, ZC. And then we are going to calculate the delta current, which is VAB, the line voltage, over ZAB. And IC delta equals VCA over ZCA. And then we can calculate the star current for phase A, IAY equals IA delta minus IC delta. So we are going to build the M code to represent these equations. So let's look here. So in line number 8 and 9, we are going to enter the voltages, but in line number 10, we are going to enter the line voltages. So we need the line voltages in this case. Line number 12, we have the impedances. So we are going to calculate in line number 14, ZAB, where ZAB equals ZA plus ZB, ZAB over ZC, and the other impedances as well, ZBC and ZCA. Then we are going to calculate the phase current of the delta, which is IA equals VAB over ZAB. And in this case, we can display that one, but we need the current for the star. So I capital A here is IA minus IC, and the same for other phases. So let's look for the results. So we have here phase currents of delta, so that one will be the delta phase currents, but we are going to look for the line currents of the star. We have the same answers, 22.5 ampere minus 33.7 degrees, and the phase B current will be 7.3 angle 2.8, and for phase C current 28.7 angle 154.9. Here there is no neutral point because we cancelled the neutral point because we converted the star to delta. But now we can calculate the power, if you like, for the star connection or from the source side. Let us confirm the results we had using Simulink platform. Let's go. This is the model we'd like to simulate. We have a 3-phase source feeding unbalanced star load with neutral wire is not connected. So I'm going to click here for the 3-phase source. We have phase A, phase B, phase C. So we have phase voltages, line voltages, and we are going to measure the 3 currents of the supply. And we have line A, line B, line C connected to the load. If you notice here, I'm going to access as well the neutral point. I tell you why now. So if we return back here, we're going to the loads. So we have 3-phase loads. That one is a star unbalanced. So if we click in phase A1, so we have resistance 14 ohm and the inductance will be 20 over omega. And for phase B, we have 25 ohm. And for phase C, we have RC. That one is very small resistance. I explained that one before. We cannot put the capacitance directly to the source. So we put here a small resistance, and the capacitance is 15 multiplied by omega here in the denominator. So 1 over omega XC. That one give you the capacitance. So I'm going to access this point. So that one is the neutral point of the load, and we call that one the floating point. We are going to measure the voltage across the load and the current going to this load as well. So if you look here, there is no connection between the neutral point of the load and the neutral point of the source. I just measured the voltage between the point N and N. So here there is no current going from this point to this point. So just measuring the voltage. So let's run. So if you notice here, we have the neutral voltage is 353.7 volt with angle minus 145.7. So let's look for the currents. From the load side, we have the currents 22 ampere. So let's enlarge that one. So we have the current here 22 ampere 0.5, 7.3, 28.7 with the angles minus 33.7, 2.8 and 155. So the currents matches 100% the calculated one or the M code. Regarding the voltages, these are the voltage across the impedances ZA, ZB, ZC. For the power, you can calculate that one if we click inside this block. So that one is I square R, I square X for each load, and then we are going to have the sigma for I square R and sigma for I square X. If you like to calculate S, so that one will be root P square plus Q square. So let's return back to look for the results here. We have here the power. For that one, we have 8.4 kilowatts and minus 2.2 kilovar and 8.7 kilovolt. So if we look from the source side, we have here the currents, the same currents, because that one is the current from the source feeding the load directly. So what do you think if we like to confirm these results? Rather than using this circuit, we are going to convert it to delta. We are going to check, are we going to have the same currents in the line or not? Let us see. In this system, we have the three-phase source we had before, VA, VB, VC, and the three currents are measured here, and these three lines are going to feed the load. Phase voltages, line voltages. You notice here we have no access to the neutral point because the load has no neutral now after we converting the load from star to delta. Let's look for the load side. We are going to calculate ZAB, ZBC, ZCA, either using manual calculation or M code. So ZAB, for example, equals 5.67 J43.3. So the resistance is 5.67 and the inductance will be 43.3 over omega. For phase B, or we can say that one is ZBC, so that one will be 12.42 and minus J23.8. So 1 over 23.8 multiplied by omega. For ZCA, we have here a resistance 26 ohm and capacitance will be minus J3.4. So the capacitance will be 1 over 3.4 multiplied by omega. So if you look here, we are going to connect the end of phase A to the start of phase B. The end of phase B will be to the start of phase C, and the end of phase C will be connected to the start of phase A. We're going to measure the voltages and line current. So line current of the delta will be the phase current of the star. So let's run. Let's check the results. We have the same currents we had before, 22.5, 7.3, 28.7 with the angles shown here. And the voltage applied to the load now is the line voltage of the star connection. Let's look from the source side. So we have the same currents because the current out of the source is going to the load, which is the delta, but that one will be a line current. I didn't measure here the phase currents of the delta. This is not my concern. My concern here is the phase current of the star, which is the line current of the delta. So we have here the phase voltages and line voltages. I didn't measure the power here because I'm just confirming that we have the same currents. So let's return back to our slides. What will I watch in video number 12? In video number 12, we are going to cover unbalanced three-phase systems, part 3. We are going to cover unbalanced source voltage, and we are going to introduce symmetrical components. See you in the next video.